one end of a light inextensible thread of length L is held stationary over a frictionless horizontal floor, while a small bead tied at the other end of the thread is describing a circular path with a uniform speed v on the floor as shown in the figure. The upper end of the thread is suddenly pulled vertically upwards with a constant acceleration a. If the bead does not leave the floor, find magnitude of its acceleration immediately after the upper end of the thread is pulled.
This is the problem given. Okay, so we are required to solve this problem. So this is the problem, and let us see this problem. So let's see the diagram first. So I'm going to draw the diagram for this problem. Yeah, this is the diagram for the problem. You can see this diagram. Now we have to solve this problem. So there is a string here. There is a string of length L, and it is held stationary over a frictionless floor. A small bead tied at other end of the thread is describing a circular path. You can see with the speed v. The upper end of the thread is suddenly pulled vertically upwards with a constant acceleration a. If the bead does not leave the floor, find magnitude of its acceleration immediately after the upper end of the thread is pulled. So this is a question taken from Pathfinder Challenge Your Understanding section. So what we have to do is we have to compute the acceleration of the small ball which is moving on the floor just after the upper end is pulled with an acceleration a. So here the concept is a little bit difficult, but we have to solve. Let us see here. I'm gonna solve this. Actually, before entering into the solution, you have to make it clear that the ball is moving in a circular path of radius small r. Let us say this is radius small r. We can take this is a right angle triangle. This is a right angle triangle with the right angle at point O. You can take sine theta. Sine theta is opposite side by hypotenuse r by L. R is equal to L sine theta. R is equal to L sine theta. So this is the radius of the circular path. Next, what we have to do? We have to find the acceleration immediately after the upper end of the thread is pulled. Okay. So let us take the problem in two steps. Step 1, I am taking the problem without acceleration a. So now without acceleration a, so the ball is moving on a floor with a velocity v. So definitely the ball will experience an acceleration which is directed towards the center. That is what we called as centripetal acceleration. So the centripetal acceleration experienced by the ball is given like this. So this is the circular path, and there is a ball. There's a ball. So here I am showing you the top view. So this is the radius of the circular path. That radius is already computed, that is smaller. So the ball will experience an acceleration which is directed toward the center. So that acceleration is a radial acceleration. So that acceleration will be in this way. So that is AR, the radial acceleration. Okay, so the ball is moving in this direction with velocity v. So you can directly write the formula for radial acceleration as v square by r. V square by r is the formula for radial acceleration. We already know that. And next, this r value is already given, that is L sine theta. So putting the value of r here, we are getting the radial acceleration as v square by L sine theta. This is the radial acceleration that we got. So I am taking step 1 by considering acceleration is 0. Acceleration of the point where the thread is held is 0. And I am going to take step 2 now. Step 2. The step 2 we can get one clarity here. The situation is different now. Let us see the situation. I will show you once again here with a diagram. So take this diagram as step 2. Okay, diagram is not coming. Let us see. Here only we will discuss. In the step 2 we are considering this acceleration also. The body is moving upwards. Suddenly thread is pulled in upward direction with acceleration a. So whenever it is pulled in upward direction, now I am going to observe whenever the thread is pulled in upward direction in this manner, this end will have some velocity. Let us say the velocity of this end is VA, and this ball will try to move in this way with some velocity VB. So I'm going to draw the picture here. Just see the picture. It may look like this. So this end is being pulled upward direction with some acceleration. So that acceleration is A, and of course it's moving upward direction with velocity VA. At the same time, so it is in contact with the floor. The ball is in contact with the floor. B is the ball and it is contact with the floor. This ball will try to move in this direction. In this direction with a velocity VB. So you can notice the angles here. We have already seen that angles also. This angle is clearly given in the problem. That angle is given as theta. This angle is given as theta, and you can see this is 90 minus theta. So this is the situation. The length of the thread is constant. It does not change. Its value is L. Its value is L. So by using the constraint equations, you can get the relation between the velocities. So I will show you how to get the relation between the velocities. Velocity of this end is in upward direction. This is VA, and this angle is theta, and you can take this velocity also. This velocity will be VB, and it is 90 minus theta. So now we are going to take the velocity components of VA and VB along the length of the thread. Because the length of the thread is constant, So the relative velocity of the point A and point B must be 0. Along the length of the thread, the relative velocity must be 0. The point is very important in solving this problem. So now I am going to take the component of velocity of VB along the thread. The component of velocity of VB along the thread will be like this. So just see the components of the velocities. I will draw the component of velocities. Velocity along this direction is VA cos theta, and this direction, the velocity component of VB is given by VB cos 90 minus theta. But length of the thread is constant, it is always L. The length of the thread is constant, it is always L. So VB cos 90 minus theta must be equal to VA cos theta. So that point is very important, because these two endpoints are moving, but the relative motion between the two endpoints is always 0. So the relative velocity is 0. So we are getting this relation, and VB is equal to cos 90 minus theta means it is sin theta is equal to VA cos theta, and VB will be VA cot theta. So now let us differentiate this equation. So dVB by dt is equal to dVA divided by dt cot theta. So dVA by dt means it is acceleration. So this is the acceleration of B, means ball. So we are having two accelerations. This is acceleration 1, that is the radial acceleration, which is due to the circular motion of the ball. And next, the acceleration, this acceleration AB, which is due to sudden pull of the string with an acceleration A in upward direction. So if you want to talk about the net acceleration of the ball, just immediately after the end A is being pulled upwards with an acceleration A, is the summation of acceleration radial plus acceleration B. Acceleration radial is already given by V square divided by L sin theta. Acceleration B is A cot theta. So this is the immediate acceleration or the net acceleration of ball immediately after the end A is pulled upwards with acceleration A. This is answer for the problem. Thank you.